Hello students, welcome to the video lectures on Chemical Reaction Engineering course 2. We were discussing on catalysis and catalytic reactors as a part of our curriculum. Just a quick disclaimer that all the slides which are presented here are an extract from a book which we are referring, that is Elements of Chemical Reaction Engineering by Fogler. Today we are going to discuss section 10.4 from chapter number 10. To give just a quick recap of what we have studied by now, we have dealt and studied on what is a catalyst, what is catalysis, its history. We have compared on to the homogeneous and heterogeneous catalyst. We have seen the different types of catalyst which are applied in different catalytic reactions. We have also studied on the catalyst properties, different types of catalyst. We have seen the application of a specific catalyst, that is monoliths, into the catalytic converters. And we have seen some basic definitions which were required in catalysis, one of being turnover frequency, turnover number. We also discussed on the different analytical equipments that are being used in characterization of different catalysts. Later we went on to study the different steps in the catalytic reaction, where we have seen that there are 7 steps. Out of them 4 are the mass transfer steps. We went on to see how we can exclude these mass transfer limitation steps and make it a pure kinetic regime. Then we went on to have a cumin decomposition as a case study, where we decided how a rate limiting step is decided and we derive a rate law corresponding to that our analysis. Today's our part of analysis or study goes for heterogeneous data analysis for reactor design. Any engineer who is going to go for a designing of a reactor goes through 4 different operations that need to accomplish this data analysis. The very first thing is we perform different experiments on a lab scale, and based on these lab scale experiments, the very first thing we have to do is develop an algebraic rate law which is being consistent with the experimental observations. Once you have this rate law, there will be multiple rate law parameters which can be rate constants and equilibrium constants based on your nature of a reaction, which you have to be evaluate or analyze and extract using the mathematical techniques. Third thing will be to find a mechanism, a rate limiting step, which is being consistent with this experimental data, and the final will be to design a catalytic reactor to achieve a specific conversion, because we'll have a parameters which will be talking on different parameters in the rate law which will apply to a certain specific reactor and design. That means we relate conversion to our known parameters. To go in details of this one by one, we'll solve all the 4 different steps for this heterogeneous data analysis and reactor design. We'll be considering a case study of hydrodemethylation of toluene. So this reaction is done over a crystallite silica alumina catalyst, and it gives you benzene and methane as a product. What we are trying to do is we wish to design a packed bed reactor where we are given a certain feed which consists of obviously toluene and hydrogen in certain percent plus inerts. Now we are given the flow rate of feed with temperature pressures, and we have to derive. Now this experiment has been done in multiple runs with multiple parameters being changed, and the bottom paragraph talks to you about the data which has been extracted. Now this is the data which has been obtained from a differential reactor where 4 partial pressures are being changed. Partial pressure for toluene, hydrogen, methane and benzene. And the corresponding change in the rate values is being noted. Now if you can see that there are multiple parameters with us which can have a dependency on rate. So if you look at section 1 and 2, here methane is changed. That means in addition to our reactants we have methane, which is a product, has been part of a feed. If you go for another set, you will see in 3, 4 and 6 you have benzene and as an additive to the feed. If you go for 7 and 9, this purely contains a reactant but hydrogen pressure is changed. And if you go on the bottom set 10 to 15, you see that toluene pressure is changed. There are only 2 runs, 5 and 16, where all the 4 components are being present and are being checked for the changes. So as a part of our study, the very first thing is we have to deduce a rate law which is consistent with the experimental data. So let us see how we can work out and look at the experimental data in a different way. If you look at set 1 and 2, in addition to the reactant we have methane, where methane is partial pressure is changed 4-fold. And if you look at the change in the rate value, it is coming out to be nearly same or a very slight change. What does it suggest to us? If it would have been other way around, if there is a dependence on a certain product, then it will come into the denominator of a rate law. But what we observed from the 2 runs, even though there has been a 4-fold increase, but we do not have any effect on the rate. So practically speaking, we say that methane is not adsorbed onto the catalyst surface so that it affects to the rate. It is directly going into the gas phase. We have seen a similar thing where a Laritel mechanism applies even in cumin decomposition. Previous case. So what we say, dependence on product methane, it is independent, or rather this value is very low. Let's go on to the second component, that is benzene. Now if you look at benzene, run 3 has only 1, then there is a 4-fold increase, and then there is a drop, and there is further increase, there is a further drop. So it's a very clear indication of inverse relation with that of the partial pressure of benzene. The rate decreases with the increasing concentration of benzene. A rate expression in which a benzene partial pressure appears into the denominator will explain to this dependence. Let's go on to the third component, which is toluene. Now if you look at toluene, when partial pressure was low value, almost there has been doubling of the rate. And as it goes on increasing above a certain value, here there is almost double, but still there has been a very low rise. If you go from 15 to 20, there has been a very slight rise. What does it suggest? That the rate keeps on increasing fast at a very low value of partial pressure, and it becomes independent or reaches a plateau when it reaches a higher value. This can be represented, we already know, something like this expression, where Pt upon 1 plus kT Pt gives you where at a very low value it will be directly proportional, and at a very high value this will get cut and you will have a independence. So now combining my previous rate law expressions, I have a relation with toluene Pt upon 1 plus KTPT for toluene, and this is for benzene. For methane, we don't have any dependence. Let's go on to the final part where hydrogen is there. If you look at hydrogen, it is 71 at 1. For doubling, it becomes double. For fourfold, it became fourfold. It suggests that it is directly dependent on pressure of hydrogen. So there is a direct relation. So our rate is going to follow a first order dependence on hydrogen. Okay. So if you combine all those things clubbed together, this is the final form of expression which we should be able to derive from our experimental data. So we have K into first order with hydrogen, Pt upon 1 plus KTPT for toluene, and this is dependence for benzene. This is what we have qualitative agreement with the data which is being available there. Let's move on to the second step, which said we have to find out a mechanism which is consistent with the experimental observation. So we have made few observations that it is dependent on toluene. So very first step has to be adsorption of toluene. Second step, because methane is not going to get any dependency, we say it remains in gas phase. It is also having a direct dependence on hydrogen. So L-aerial mechanism we suggest. Hydrogen with toluene occupied sites goes benzene on the catalyst surface and methane goes out. And finally desorption of benzene in the gas phase. Now we have already discussed that there is 90% of the chances that most of the reactions are surface reaction limiting. We consider here the same thing for surface reaction limiting. So we have to derive this surface reaction rate law. Now if you see, there are two things which cannot be derived, that is occupied sites by toluene and occupied sites by benzene, which we have studied before. That how do we get it? Because the surface reactions rate limiting is the slowest step, and hence adsorption rate is very high. Leading rate of adsorption upon Ka goes to 0, which will give you the occupied sites by toluene. On the other side, we have rate of desorption upon Kd also goes to 0, which gives you site for benzene. But both of these expressions have vacant sites. And these vacant sites are being derived through the total site concentration, where we take a balance of vacant sites plus occupied sites by benzene and toluene, which gives us the final expression. Now using CTS, CBS and CV, you can get the final form of rate expression of surface reaction, which leads to finally, if you neglect the reverse reaction, you get P of H2PT 1 upon K, which is what we have derived also from the, and consistent with that, our experimental observations. That led us to your third step. What are the parameters which should be come out from this, which we don't know? Is the rate constant, which we said it is a combination of some lumped parameter of multiple rate constants and equilibrium constant, and then we have equilibrium constant of benzene and toluene. We need to rearrange a rate law in such a way so that we obtain a certain linear relationship between the variables. We do so by reshuffling this expression into this way, and then we can apply a regression analysis techniques which can determine our rate law expressions. Now this is our one dependent variable, second, and these three parameters we have to derive. Now based on the regression analysis method, you will be able to get this. These are the parametric final evaluation. You can do the step-by-step regression procedure which you have studied in your mathematics. course. If not, you can follow to chapter number 5 to get those analysis done. Polymath will help you to do this regression analysis based on the initial values. Now we have evaluated these three parameters, that is K, KT and KB. That takes us to the last step of our analysis, that is reactor design. So we have a packed bed reactor design equation which relates conversion to the rate law. So we have all the partial pressures equation with us, which is going to relate using this, where dx by dw is minus Ra upon F0. Now to go for this reactor design, we'll have a quick look on example number 10.3, where a fixed bed reactor design has to be done. That will end our complete process. To also discuss on the hydrodimethylation of toluene, which is being done in packed bed reactor, we have to find out conversion as a conversion to pressure and the partial pressures of with respect to the weight of catalyst. What we are given is, we are given molar feed rate, we are given reaction conditions, we are given feed composition. In addition, we are given a pressure drop parameter which is alpha. We also have to determine the catalyst weight here. The underlined in green are the given data and underlined in red is what we have to find out. For a bulk density of a catalyst, we have to find out the catalyst weight. So how we are going to do this? Let's go on. As our usual procedure, we write the reaction first, which is hydrodimethylation of toluene. Reactor is packed bed. For packed bed reactor, this is the design equation which we have. To solve this equation, we need polymath, a differential equation. What do we need is RT dash. What is our rate law? Our rate law is in terms of partial pressure of benzene, toluene and hydrogen. What are the values of these parameters? We have already derived it from regression analysis, so you have those parameters. Now the question comes, how conversion relates to this pressures? That is what we want. So your partial pressure of toluene becomes CRT. You convert it into, because it's a gas phase reaction, but again 2 moles are giving of 2 moles, so your absolute epsilon, that is the goes to 0. So this part goes to 0, and what do you get is PT as PT01 minus X. Now because we are going to use packed bed reactor, we have an additional parameter here which is Y, which we are going to discuss ahead. Now this is as far as PT is concerned, hydrogen. Because if you have carefully seen, we have 30% toluene, 45% hydrogen. It's not an equimolar reaction anymore, not the same percentage. So you have hydrogen is M minus X, or rather theta, which is the ratio of hydrogen to toluene available with us. Now if we look ahead, then we need one more pressure, that is P. B, which is from the product stream, so that becomes PT0 and 2x. Everything is multiplied by a parameter which is Y, that is a pressure parameter, pressure drop term Y. And for a constant density system, or where epsilon is 0, the pressure drop term for a packed bed reactor is given by this term. This alpha parameter, the pressure drop parameter, is also given to us a certain value. Now let me clarify a few terms into the problems which were given. We were given PT0, which designates the initial pressure of toluene. However, what we are given is total pressure of a reaction, which was about 40 bars. And what is the P? It is the initial mole fraction. That is the final pressure which we are expecting here. Now if you look for PT0, this becomes, because fraction is 30%, it becomes about 12 atmosphere is partial pressure of toluene among the total pressure of 40. So let us think on to the maximum catalyst weight which we need to have and not fall below 1 atmosphere. So we are taking P as 1, P naught we are given as 40, and that is where we'll be able to evaluate the weight of catalyst, that is about 10 tons. So this gives you the limit to what weight you should be following. So this is where we have everything ready. We have a differential equation, we have a rate law. The rate law, we have pressure terms. Pressure terms were represented in terms of conversion. They had a pressure drop parameter from packed bed, which is also given in terms of weight and alpha. All the explicit equations are well defined to get you the which are needed to support the differential equation. Once you go through the run, this is what the final result do you get. You have a rise in conversion with the weight in the packed bed which goes to 60%, while the pressure drop term will go down to 1 by 40 along the weight. And if you look at the pressure terms, this is how benzene will go and come drops. So this is what expected as an output or result from your question. So this is what we have learned through our video lecture. We have seen the heterogeneous data analysis for a reactor design considering a very specific case of toluene hydrogen demethylation. We have developed a very rate law consistent with the experimental results. We have found out a mechanism based on our instance how and what should have been done after we have developed this rate law. We have analyzed this rate law and extracted the rate law parameters from regression analysis. This we have applied with the given conditions and specifications in a problem to design a packed bed, where we have come out with the profiles of conversion with the weight of catalyst. Also the partial pressures change with the weight of catalyst. So that ends to what we were doing in this video lecture. Thank you for your kind consideration and patient listening. We'll be continuing next lecture on deactivation of catalyst after this. Thank you.